So in the last class, so first of all, the exam. So if you have not heard already, the exam will be on next Monday. All right. So last class, I told you how to identify the element by looking the spectra, right? So people have collected a lot of spectra of many elements, many compounds, many chemicals, whatever they could find, and they make the database. They make the database, and you can access those database in the government website or the big laboratory websites, big universities website, and first of all, what you do is you take some samples. Let's say somebody give you some sample here. This is a sample. Let's say it could be copper, it could be iron, it could be manganese, it could be magnesium, or it could be anything, right? So we don't know what is here. So we want to find what is here. So what we do is we take some sample and put in the tube. We put in the tube like this. Put take some of the sample and put these atoms here and vaporize them, and we just supply some electricity in this tube, right? And once we supply the electricity here, these atoms start to produce the light. So they produce the light, and we put a prism here. This is a prism, and the light coming here, we pass here, right here. And then this prism, what it does is it divides this light into many parts. 1, 2, 3, 4, 5, 6. How many kind of light it gives? It's divide like that. And then this light, maybe we look at nanometer. So what is the wavelength of this one? 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 And we put this wavelength in this. It's a chart. It's just like the pH paper or something like that. It's a chart, yeah. So this is this one. 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 So the upper one comes around here for the red side. So this is the red side. This is the violet side, and this number will be exactly same for the. If it is a copper, let's say if it is a copper, maybe this is 200 nanometer. So let's say it is 700 nanometer here. Maybe this line is in 500 nanometer. Maybe this is 350 nanometer. Maybe this is 200 nanometer. So it comes like exactly number comes like this. And then we take this our spectra and compare the government data, government website data, yeah, or the other labs data. And if our spectra matches exactly with their data, and then we identify that this is a copper, yeah. So this kind of spectra is copper. So this is already done by other people, and this is exactly matching with this one. So we say, okay, so their data is this one, our data is this one. This one and this one exactly matching. So if that is copper for them, this is copper for us. Make sense? So this is how we identify the element by spectroscopy. This is a very powerful technique in chemistry, physics, biology, medicine, whatever you work. So spectroscopy is the most powerful technique to characterize the elements. And you can also calculate by looking the spectra their intensity and how much copper is here, or in solution how many milligram per liter copper is there. So you can just identify those two. Yeah. So like this. Now, in the slide number 8, I have a couple of things here. So ground state. What is the ground state? So let's say we have an atom of something, and this is the first orbit. So this is the nucleus. When nucleus, we have proton and neutron, and this is the first orbit, and we have other orbit around here, and the electrons are revolving around the nucleus in this orbit. So if the electron is in the first orbit, we call that's a ground state. Yeah. So the ground state. But if the electron has moved to the second orbit, or third orbit, or fourth orbit like this is called the excited state. Yeah. So ground state, the lowest energy level. So when the electron is in the first orbit, it is called the ground state. If the electron is in the higher orbit, we call that as the excited state. Now I told you the energy of the electron is given as negative number. So energy of those electron is given as minus RFC by n square. So like that one. So this number here comes to be very big. this number is small, this number is small, and this number is small. So the higher electron level, exactly, the higher electron level is the more energy. But if you look the number in the book, it looks like this is a small energy, but it's not true, because the energy of the electron is given is a negative number. So this is a very small negative number, and this is a very big negative number. So this is the smallest number, smallest energy. This is the highest energy, like that. So when the energy is zero, so when will the energy of the electron is zero? So when electron is completely off, so up to here it is influenced by this proton here. This is positive charge, this is negative charge. So this is still attracting this one, and it has some large energy. But if you give energy, very, very high energy to this electron, for example, let's say this electron is this electron is here, and you give the light to this electron, the very high frequency light. This is the light, so this represents the wavelength here. The very high frequency light. What it does is it strikes this electron and knock completely out from the atom. So this electron may jump here, may jump here, may jump here, or it completely leaves the atom and go fly away in the air. Make sense? So in that case, the energy of the electron is zero. So when the electron just leave this atom and go somewhere here, in that condition, the energy of the electron is called zero. Make sense? So when the electron E is equal to 0, electron completely separated from the hydrogen nucleus, meaning that when the electron is here, energy is not zero. When the electron is here, its energy is not zero. It's more. Energy is more. It's more. So more. But now if the electron completely detached from this atom and go out, then this is called the electron has zero energy. Make sense? It's just a counterintuitive. So we are used to thinking the plus sign. Plus 5 is more, 4 is less, 3 is less, 2 is less, 1 is even less, 0 is even less, right? That's how we used to be thinking, right? But here, when we talk about the energy of the electron, it's just the opposite, because they give the negative number here. So this is the highest. So highest basically is a 0. So when electron has a very, very high energy, that is the 0. That just detaches. So 0 energy of the electron looks to be very, very high. Make sense? But if you are talking in other cases and you say, oh, I have a 0 energy, that's bad, right? So if electron has a very high energy, it detaches from the atom, and that energy of the electron is called the 0 energy. So 0 energy is the highest energy, and this energy is a high energy. This is a little low, this is little low, and this is the lowest energy. That's how we interpret the energy of the electron. Yeah. So long time people started to do that, and probably nobody corrected, or maybe there is no way to do correction. So they just put the energy of the electron as a negative, and 0 is the highest energy of the electron. It just detaches. If you give a sufficient amount of the energy, electron just detach and go out, and that is the highest possible energy, 0. Yeah. See, it's a little bit counterintuitive. So now I'm in the slide number 9. So here is an example. So I'm just doing a math there. So this is the atom. So this is the atom here, and then this is the atom. It says calculate the energy of n is equals to 1. So if the electron is in the first orbit here, n is equals to 1. So how much energy is here? So energy 1 is given as minus RHC by n square, right? This is the formula to calculate how much energy electron has, right? So we just put minus, the R value is 1.09 10 to the power 7. H is 6.62 10 to the power minus 34. I already did this, you don't have to copy here, so it's already done in the slide here. So C is 3 multiplied 10 to the power 8 meter per second, and then n square. So n square. So let's calculate E1. So for E1, I put the value of n is 1. So let's calculate this one first. So if you multiply RHC, this one, and this number here, you get 2.16 10 to the power minus 18. So 2.16 10 to the power minus 18 by n square. So this is our formula for the calculating the energy of the electron. Make sense? So one electron. So we are calculating the energy of the one electron. So RFCs always give this one. So once you calculate this, multiply this number, you don't have to repeat. This always comes to the same. Make sense? Good. So now let's calculate E1. So this is E. Let's say this is E. Now I'm going to calculate E1. So how much is E1? E1 is equals to 2.16 10 to the power minus 18. Now 1 means this is 1. N is equals to 1. 1 square is 1. So that's 1 square. And put this number in the calculator. The calculator says that much. Minus 18. So if the electron is in the first orbit, that much is the energy of the electron. Make sense? 1 electron. Now let's calculate the energy of the second. If the electron is here, not in the first orbit. Let's say electron was here in the second orbit here. So the E2 would be 2.16 10 to the power minus 18. So this is minus, so you can put minus here, divided by n square. So n square is here, n square, n is equals to 2. Now 2 square is 4. Yeah, 2 square is 4. So how much is the energy here? So divide 2.16 by 4 in calculator, and you will get negative 0.54 10 to the power minus 18. In the book, you might see 10 to the power 19 here, so don't do that. Sometimes you don't know how to compare 10 to the power minus 18 and 10 to the power minus 19. So just always put 10 to the power minus 18. Yeah. So just always put like that. And so you see now, if the electron was here, the energy is very small, minus 2, 10 to the power minus 18. But if electron is in the second orbit, energy is high, just minus 5.54. So this 0.54 is higher number than this minus 0.16. Make sense? So that's what I was trying to say. So I was always confused when I was a student. I was always confused. How is it possible that this is a small number and this is a bigger number? But you look the sign here. So minus 2 is a very small number. Minus 0.54 is bigger number. So in second orbit, energy is higher. Now if you want to calculate the energy at third orbit, you can put 3 here. 3 square is 9. So divide 2.16 by 9 and you get third. And if you want to calculate energy in fourth orbit, put 4 here. 4 square is equal to 16. 2.16 divided by 16 and calculate that at that many joule 1 electron. Make sense? Yeah, very simple. So now, what is the difference between energy of second orbit and this orbit then? So let's calculate the energy difference here. So I got the energy in 2. If the electron is equals to 2, I got the energy. If the electron is 1, I got the energy here, right? Now what is the difference? How much difference is the energy? For example, if the electron jump from here to here, how much energy it absorbs? Or if the electron jump from here to here, how much energy it released outside, right? So that's what we want to calculate, the difference, right? So the difference. So how much is the difference? We give the difference by delta E. Delta E is equals to, you can do E1 minus E2 or E2 minus E1, it doesn't matter. Whatever you want to do is the same thing. So E2 minus E1. So that is, so E2, let's put this bigger number first. Minus 0.54 10 to the power minus 18. This is E2 minus the E1. So E1 is, so let's put like this. So this is E1 minus the, this is E2, put E1. E1 is minus 2.16 10 to the power minus 18. Now, if you see here, you really don't have to do 10 to the power 18, 10 to the power 18 because it's the same number. So you could also do like this, 0.54 minus 0.54, minus and minus is plus here, 2.16, and you could just put 10 to the power minus 18. Like this, so that maybe calculation becomes easier. But it is up to you because once you put in the those number in calculator gets the answer. Yeah. So now, so this become plus, this become minus. So the difference would be 2.16 minus 0.54 would be how much is that? So 1.62. So 1.62 10 to the power minus 18. So this number never comes above 2.16. So bigger, the number you get here will be never bigger than the bigger number here, right? because we are just getting the difference, and the difference is always a small number, right? See, this because of this minus sign, a little bit confusing. But remember here, if it is one is a minus here, another will be plus. If you put plus here, you put minus here. It doesn't matter. Yeah. So this is 1.62 10 to the power minus 18 joule difference in energy. So if you put in this electron, if you put 1.62 10 to the power minus 18 joule of energy, this is going to jump from here to here. Yeah. So that means that, or if the electron is in the second orbit, if it jumps from second to first, it is going to give us 1.6 to 10 to the power minus 18 joule of energy. So the difference has that significance. Yeah. So why difference? Why we are interested in difference? Because that's the energy. Either the electron is going to absorb if it jump from inner to outer, or it is going to release that much, the difference amount of energy, the different this amount of energy if it jumps from here to here. So you can just follow the same rule all the time, and you can calculate what is the difference of energy from here to here. So calculate the energy in third and calculate the energy in first, and then subtract from here to here, and you get the difference. Yeah. Good. So that's how we calculate the difference in energy. Now, I'm just talking about the one atom. We are just talking about one atom, right? Now, let's talk about the 1 mole of atom. Maybe in the experiment, we cannot take one atom, because we must take 1 mole of atom, 2 mole of atom, 4 moles of atom. So that means, let's say 6.023 10 to the power 23 hydrogen atoms here, and do the experiment. How much energy would it be? So you need to multiply this by this number. This is the energy of one electron. In 1 mole, there are that many electrons. So this multiplied by this number will give you the energy of the 1 mole of the electron. Make sense? So just put those numbers in calculator, and I already did it in the PowerPoint slide. Just multiply this number with this number, and you get the energy of 1 mole of electron. 1 mole. So 1 mole of electron. So this is the energy of one electron. This one, 1.62 10 to the power minus 18 is the electron energy of one electron. So if we have 1 mole of electron, that is, if we have 6.023 10 to the power 23 electrons, how much energy difference that would be? So this multiplied by this. So that will give you 980, 9.8 10 to the power 5 joule, which is 980 kilos. It doesn't matter. You can put whether in joule or in kilos. Yeah. Good. So this equation, this is one way of doing things, but there is another equation later I will show you, exactly gives the same answer. Yeah. So this is one way of doing. There is another way of doing things, the difference also. So we are done here. So this is 980. Now I start the third lecture in the canvas I posted. So in the first slide of the third lecture, we have mathematical Bohr model. Mathematical Bohr model. So let's see. So up to here, only John Balmer and other people were doing this kind of thing. Now, what Bohr said is this one. So he did a lot of mathematics and assumption, and he gave this equation. So this is, I think you may like this equation than previous one. Delta E is equals to, he gave this equation, 2.18 10 to the power minus 18 joule 1 by n f square minus 1 by n I square. So this equation and what we did in previously E2 minus E1 is exactly the same thing. So this is given by Bohr, Niels Bohr, the previous equation that we found the delta E by doing E2 minus E1, the previous people did that one, but both way give the exact same answer. Make sense? So what it is saying is that, so this is the constant. So basically this number is exactly like the RHC value. So if you multiply the value of the Rydberg constant and this is Planck's constant and the velocity of light, and you are getting a number previously was 2.16 10 to the power minus 18. So previously when you were multiplying R, H and C, you were getting here what 2.16 10 to the power minus 18. But Bohr said, a little bit I've changed. So he said 2.18. So how big number 2.16 and 2.18 is exactly same, right? So it basically is like the RSC value. So either you do this way or that way is the same thing. So what is NF? So NF is the final. So let's say, so you have a nucleus here. This is a electron in the first orbit. This is in the second orbit. So let's say at the beginning the electron is in the second orbit. N is equals to 2. N is equals to 2. Now it jumped back to 1. It jumped back to 1 here. So from here it jumped back to 1. N equals to 1. So this one they call initial. So at the beginning, electron was at the first orbit, right? Second orbit. They give initial for this one. And then the electron jumped to the first orbit. So they give this as the NF. But it doesn't matter. You put either 2 here or 1 here, 2 here, or 1 here, you get the same number. Yeah? So don't get confused. So electron is jumping from 2 to 1. So the difference, we are just interested. How much energy it would release if electron jump from here to here, or how much energy it would absorb if electron jump from 1 to 2. So we are basically interested in calculating the difference of energy between n equals to 1 and n equals to 2, right? So let's put the value here. So it's very simple. 2.18 10 to the power minus 18 joule. 1F, so final. So electron was at the beginning. Initially, it was in 2. Now electron jump from 2 to 1. So NF is final is 1. So 1 value of this is 1. 1 square minus electron was in the second orbit at the beginning. So 1 by. So this is Ni is 2 square like this. But some reason you get confused in exam and you put 2 square here and 1 square here. Answer will be exactly the same. So maybe there you will get some negative sign and you just remove that negative sign. Make sense? The answer will be exactly same. So what I'm saying is we are just concerned about 2 and 1, and you should have put exactly 1 here and 2 here, but for some reason you just get confused and you put 2 square here and 1 square here. Would it the answer be difference or same? It will be exactly same. So don't get confused. So you will not make mistake by putting this way or that way. Yeah. Good. So now how much is this one? So this is 2.18 10 to the power minus 18 joule, and then this is 1 by 1 square is 1 minus 1 by 2 square is 1 by 4. 1 by 4 is 0.25. So calculator will do this kind of thing. Yeah? Make sense? Yeah, so 2 square is 4. 1 by 4 is 0.25. So this would be 0.75. So that will be 2.18 10 to the power minus 18 joule. This is multiplied by 0.75. And how much value you get is so I'm doing 1 to 2. So in this slide there was a 2 to 4. We will do the 2 to 4 also later. So you will get a number here. So that is the energy difference between 2 and 1. Make sense? Good. Now in this slide I am so it's a 4 to 2. So this question is, suppose the electron jumps from fourth level to second level. So look the slide number 1, fourth level to second level, right? So let's do fourth level to second level. So I was doing second level and first level here. So let's do fourth level and fourth and second. So how much of the energy there will be? So electron is jumping from this is nucleus here, n equals to 1. Here n is equals to 2. Here n is equals to 3. Here n is equals to 4. So 4. So electron is jumping from 4 to fourth level to second level. Suppose the electron jumps from fourth level to second level. So electron was here at the beginning. So that is the n initial, and then electron jumps here and final here. So this is make sense? So very simple. So 1 minus NF is what? So final. It jumps from here to here. In the final orbit is 2 square here. And then initial orbit is electron was in the fourth orbit. So 1 by 4 square. So put this number in calculator. So 1 by 4 would be 0.75. 1 by 4 square would be 16. 1 by 16 would be, calculator will give all, just multiply. Make sense? Very simple. So, would the answer be different if you put 4 square, 4 here and 2 here? No, it will not. Maybe there you may see a negative sign. Just remove that negative sign. Yeah? It will not make any difference whether you put this way or this way. It's just like would them let's say 5 minus 2 or 2 minus 5. It gives the same number, right? 5 minus 2 is 3, 2 minus 5 is minus 3. They are basically the same number, right? So it's just like that. So if you get, if some reason you just get confused and put 4 here and 4 square here and 2 square here, you may get negative sign. Just remove that negative sign from there, and you get the positive sign, because the energy difference cannot be negative. Yeah. So don't get confused this one. Good. So like this one. Now you calculate the energy difference. Now how about the frequency? Let's say how much we got here. So the energy, if the electron jump from 4 to 2, how much energy it releases? So if I calculate this one, I get 0.408 10 to the power minus 18. So if you look the book, they might write 4.08 10 to the power minus 19. But that I just find a little bit harder working that way, so I always put 10 to the power minus 18 all the time. Yeah. So in the book they might write 4.08 10 to the power minus 19. But rather doing that, I just write whatever the calculator gives in the front number. I just put that there. Yeah. So this 0.408 10 to the power minus 18 or 4.08 10 to the power minus 19 is the same thing. Yeah. Good. So that much is the energy released if the electron jump from 4 to 2, just like this. So like this. So the way this peak to peak, this the wavelength, and the number of these peaks gives the frequency. Now let's calculate the from this energy difference. What is the wavelength of this light here, or what is the frequency, right? So let's calculate that one. So you already calculate the energy. Now So we got the energy here. So energy difference, you can write delta E or E, it doesn't matter. 0.408 10 to the power minus 18 joule. So that much is the energy difference. Now look back to your note. So we were doing this. Energy is equals to H nu, right? The Planck's constant multiplied by the frequency, right? Now if I convert this nu to the wavelength and velocity of light, the E would be the H, so it would be C by lambda. So C is the velocity of light, and the lambda is the wavelength. This is the peak-to-peak distance of the radiation when the electron jump from 4 to 2. So like that. So I put this number here, H C, basically Hc by lambda. So E will be Hc by lambda. So 0.408 10 to the power minus 18. Now I need the lambda. So what I would do is I need to calculate the lambda. So I would put just 1 by lambda here. I would pull this H and C down here like this, 0.408 10 to the power minus 18. So if you put Hc here, that H and C comes here. The value of H is 6.62 10 to the power minus 34, and then value of C is 3 multiplied by 3 10 to the power 8 meter per second. So I put the value of H and C here, right? Make sense? Good. Now you just put in the number, and 1 by lambda would be equals to, you get some number there, and put in the calculator and find the lambda as 486.2 nanometer. So if the if the electron jump from 4 to fourth orbit to second orbit, he gives out this kind of the light, and if you measure the peak to peak distance of this light from here to here or another peak to here, so that is 482.2 nanometer. Make sense? Yeah, just play with the calculator. Just put the number and find the lambda value. Yeah. So I will put the one homework here. So this way or how I did previous way is the same thing, exactly same thing. So it doesn't matter what way you do. Or there is a Bohr's equation. If you, sorry, the Balmer equation, the very first equation we talked in this chapter, 1 by lambda is equals to 1 by, whatever the number, 1 by 2 square and then 1 by n square, or something like that. So either you use this equation or that equation, and then I think there was one number here, Rydberg constant. So all give the same wavelength. Either you use the first equation. Which one I used was I don't know, where was that? Yeah, 1 by lambda equals to r, 1 by 2 square. This one is 1 by n square. So any equation you can use to calculate the wavelength. Either you can do the energy wise like this, and then convert that energy to hc by lambda, or you could directly do this also. 1 by lambda is equals to r, 1 by 2 square minus 1 by n square. So this is the Balmer equation. So you can use also this one. So what is the lambda if energy? What is the wavelength of this one when electron jump from 4 to 2? So basically, so 1 by lambda, you want to calculate the wavelength, and r 1.0709, 1.0974 10 to the power 7, and then 1 by 2 square will be 1 by 4, and then 1 by n square will be, another will be 4 there, so 1 by 16. So if you do this one also, the lambda, you would get 200, how much? 400. Was that? So if you do that also, you will get the same value. So either you use this equation or the another that I did previously, and you get the difference and convert energy as a hc by lambda. So all give the same number. Yeah. So once you know one equation, it can do all the right. So because different people give different things, so in the honor of other people can't remove their equation. So although so first guy got one way, and another guy got another way, and another guy got another way, so that it's all this kind of the equation. But as a student, we really don't have to understand everything, right? We are just interested how much energy is released what is the wavelength of the frequency of the light when the electron jump from 4 to 2 or 3 to 6. It doesn't matter which one. Yeah. Good. So it's the same thing. Now, so it is too much thing. So it is too much thing. We don't really need to study that much to work in life. So if you go to work in the company or industry or the research lab, you just take one thing and just keep repeating the same thing. You don't study, oh, this guy did this thing, this guy did this thing, this guy did this thing. So we don't do that, right? We just do one thing all the time. So I was working in a battery research field. So my job was just to go there and change a tiny bit of thing and make battery and put in the instrument, and the instrument would do the job. So all these things I teach and I study, I never use those. So we never use this kind of thing when we go to work. So we just use one thing. Yeah. So now, how much time we have? 9:34. We still have some. So we just finished the how Bohr derive the model and give us an equation. So that equation we could use to calculate the difference in energy. All right. So now we go to the slide number 2 of this third lecture. So there is a wave-particle duality, WAVE, wave-particle duality, particle duality. So now it's becoming complex, wave-particle duality. So I already told you a little bit in previous lecture. So if it is a wave, so let's say something is behaving as a wave. So let's say this is a light, and this light has peak to peak distance. So peak to peak distance, that's a wavelength. And how many peak per second? So so we have wavelength, and peak peak to peak distance is wavelength, and how many peaks per second like this, how many peak per second here pass through one point. So we give the frequency, and then this is called the wave model of material, right? This is the wave model of material, and a long time ago, people thought light behave like this way. So this is the wave. But later Planck said, okay, so this light is behaving as a wave, that's okay. But light sometimes behaves as a particle like this. So let's say there is a source. The source is giving me not light, not as a wave, but is a photon, like the packet of energy. It's just throwing 1 photon, 2 photon, 3 photon, 4 photon, like that. Yeah. So like this. So like this. So light behaves as a wave here, but light here is behaving as a particle. So this is called the wave-particle duality. Sometimes if we do one experiment, light shows like the wave, like the water wave. Yeah, like the water wave. So go to the river and look the wave. So something is falling there, and you see the wave rising and falling, right? So sometimes light behaves like, but another time light is just coming as a ball, 1 ball, 2 ball, 3 ball, 4 ball in another experiment. So if you do one kind of experiment, like there is a wave, if you do another experiment, it behaves as a particle, right? So this concept is called the wave-particle duality. A thing is there, it sometimes behaves as a, in one experiment it behaves as a wave, in another experiment it behaves as a particle. So this is called the wave-particle duality. So electron basically is a particle. So this is the electron moving around the nucleus. So this is a particle. It's a particle. So we think this is a particle. But the people think that, oh, if you do some other experiment, this particle, this electron might be behaving like a wave. Kind of bizarre, right? Yeah. So I don't know what really this means. But when people do the experiment, one kind of experiment, the same thing behaves as a wave. They do the another kind of experiment, the same thing behaves as a particle. Bizarre, right? So this is called wave-particle duality. So let's say matter has a wave properties. The wavelength of the matter is given by de Broglie equation. So a guy named de Broglie give the equation, this equation. So lambda is the wavelength of particle wave, and h by mass multiplied by the velocity. So this is the velocity. So this is the Planck's. So this is the wavelength of particle. Wavelength of particle, like me. Wavelength of particle. And this is the Planck's constant. Planck's Planck's constant. So Planck's constant, that is 6.6 to 10 to the power minus 34. And this is the mass of that particle. What we are talking about. If we are talking about, this is the mass of the electron. If I am talking about a pen like this is the mass of the pen, right? So mass of that particle, and this is the velocity of the particle. Velocity of particle. So basically, I'm like a particle, right? We are like a particle. We are not wave. We are not behaving like the water wave, right? We just look each other as a particle, right? It's a one thing. So how much is the my wavelength now? So I'm moving with a certain velocity now here, right? I'm just moving this way or that way. So I put that velocity here. And what is my mass? So my mass is about 60 kilograms. So I put 60 kilograms here. 60, and the velocity, how much I am, my velocity here, right? My mass and my velocity here. And what is h? H is 6.62 10 to the power minus 34 joules second. So you multiply and this calculate these all things in calculator, and whatever the number comes, that is my wavelength now. So everything has a wavelength. So how much wavelength? Why we can't see? Why you can see my wavelength? So we talk about that thing later, yeah. So why, if there is a big thing, we can't see the wave. We can't see like the wave. So you are just sitting there. I'm just looking you as a particle. You are just sitting there, not doing like the water wave, right? So why I can't see your wave now? So we will do one problem here, and that will explain those things. So let's do one problem here. So in example number 3, so although we all have a wave, but we can't see our wave. Why we can see our wave is here. We can calculate. So calculate the wavelength of a golf ball. You know the golf ball, right? The golf people hit the golf ball, right? The big I think it's a green balls, right? So that's a golf ball. So golf ball. Let's calculate the wavelength of the golf ball. So the golf ball has mass of 82.5 grams, and the golf ball is moving with the velocity of 255 kilometer per hour, right? So like that. Now I have mass and I have a velocity. Now velocity must be in meter per second. You need to convert this kilometer per hour into meter per second and gram into kg. So kilogram. So convert this into kilogram. That will give you 0.0825 kg. Yeah. If you don't know how to calculate, you just put in the Google calculator gram to kilogram. It's there, but the conversion factor is this. So 1 kg is equals to 1000 gram. So by using this conversion factor, you can convert gram into kilogram, and this is that many kilogram. And then you can convert this meter per second, kilometer per hour into meter per second, and that would be 70.83 meter per second. So now we have mass and velocity here. Now what is the mass? What is the wavelength of the golf ball? So the wavelength of the golf ball, lambda, is equals to h by mv. So h by mv. What is h? 6.62 10 to the power minus 34, given by Planck's constant. What is m? So 0.0825. 0.0825. What is velocity? 70.83. So that much. So that comes in meters. So this is 1.13. 10 to the power minus 34 meter. 34 meter. You see, the golf ball has that many, that is small wavelength, tiny. 10 to the power minus 34 is a really small. 10 to the power minus 34 is even not a point, right? Very small. So can your eyes see the wave, golf ball behaving as a wave? It cannot. You just see the golf ball is a particle moving in the ground, right? You can see golf ball as a water wave, like giving rising wave and falling wave, rising wave and falling wave. Why we can't see those rising and falling wave of the golf ball? Because it has a really small wavelength, so we can't see with our eyes. Make sense? So all of us has particle characteristics. You already know we are particle, but we are also like the vibrating wave. So we are just waving, and we have wavelength, but that wavelength is really small, so we can't see our wavelength. Yeah. So that's all about this one. Now let's talk about one thing. Calculate the wavelength of an electron now. So let's do in the slide number 4, and we finish this lecture. Slide number 4. So for the golf ball, we can't see the wavelength of the golf ball. We just see it's the particle because the wavelength of the golf ball is really small, 10 to the power minus 34 meter. Now, slide number 4, we have calculated the wavelength of electron. So what is the mass of the electron? The mass of the electron is 9.11 10 to the power minus 28 gram. So convert this into kilogram. So that will be 9.11 10 to the power minus 31 kilogram. So just put in the calculator, yeah. So 1 gram is equals to 1 kilogram equals to 1000 gram, and you can easily calculate. So what is the velocity of the electron? So velocity of the electron is given as 3 multiplied by 10 to the power 7 meter per second. So this is good. It's not in kilometer per hour or mile per hour. So it's already good in unit. So grams will be converted in the kilogram. So calculate the wavelength. Now wavelength lambda of that electron is equals to h by mv. So value of h is 6.62 10 to the power minus 34. Mass of the electron is 9.11 10 to the power minus 31. Velocity of that electron is 3 multiplied by 10 to the power 7. So put this number in calculator and you will get the number, how much you get? 2.43 10 to the power minus 11. 10 to the power minus 11 is not that small number. It's a pretty big number. So the wavelength of the electron can be seen in the experiment. Listen. So previously, when we were doing the golf ball experiment and we calculate the wavelength of golf ball was 10 to the power minus 34 meters. So really small. No matter how good instrument we make, we cannot see golf ball as a wave because the wavelength is really small. So I can't see the wavelength of the golf ball as a wave, so like the water wave, right? Now, but the electron, its mass is pretty small here. So the mass of this electron makes the whole wavelength very big. So 2.40 10 to the power minus 11. So if you have a good instrument, you can see the electron behaving as a water wave, like the wave, just the waving. Yeah, makes sense? So if the thing is big, the wavelength is very small. We cannot see. If the thing is really tiny, we can see. We can measure the wavelength. Make sense? So I think we learned a lot here. So how much time we have? 46. So let's touch this one more thing and then we finish. Heisenberg uncertainty principle. It's bizarre. You see, it's something people are just thinking something like this, right? Now, let's do one thing here. Heisenberg uncertainty principle. So this is Heisenberg. It's a German scientist, H-E-I-S-E-N Heisenberg. So Heisenberg is a guy who gave this principle, Heisenberg uncertainty principle. Uncertainty principle. It is said that nobody in the universe or in the world understands this principle. What is going on here? So there, if you look the popular article in different newspapers, they keep talking about this Heisenberg uncertainty. What is it? What is it? So everybody is just saying that what is it, but nobody really understands what is it. Yeah. But we study in this class and we study in the very high class. People do PhD, do research, but still people can't give the conclusion what really it is. Yeah. So Heisenberg uncertainty principle. So what Heisenberg said is this. So this is subatomic particle. So tiny particle, very tiny particle. So it is moving. It is moving with a certain velocity. Like this, it is moving. Now, if you try to look this one, where it is, now its velocity changes. You see, just it was going like this, and just you sit there and look it. Once you look it, its velocity changes. Yeah, where it is? You just try to find. Okay, where is it? Where is it? You're just trying to look. Where is it? Okay, it is here. So you're trying once. You just try to look. It just disappears. Its velocity just changes. Yeah. So something like this is called the Heisenberg uncertainty principle. So if you try to locate this electron where it is, you cannot measure the velocity. Its velocity immediately changes. Yeah. So before you observe, nothing was happening, right? Now you observe it, and that electron start to behave weird way. So this is kind of the observer effect. Yeah. So just like you are doing your own thing, and you are just so happy there, and I as a teacher, started to carefully look at your face, and immediately you started to change your face completely. Now your mood is completely changed, right? It's just like that. Make sense? So let's. My battery is down, so we are almost done here. So we will do in next class. Yeah. Good. All right. Thank you very much, everyone. So next class is next Monday is the exam. So prepare for that.